Hi, my name is Rogério da Silva, and this is the section 4, is the test design techniques. So make sure you watch all the videos, and they are, again, these same as the others, they are short videos, so you can always go back to each different sections and watch it over and over again. Make sure you go all the way to the end, where you're going to find some quizzes there where you can practice the section. Make sure you will memorize and familiarize with this section. And again, you'll be fine. You will pass on the exam as long as you follow follow the instructions, and follow the quiz. Practice, 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 and you'll be fine. Okay. So what we're going to be talking about in this fourth section, we're going to be talking about identify test conditions, build test cases, about test procedure, know the test coverage, test case design techniques, black box, white box, and experience-based techniques. We're going to talk about specification-based techniques in the black box option, structure-based technique, and experience-based technique in more depth. The test development process. The test development process is a breakdown of the analysis and design phase discussed in section 1. It can be done in different ways, from very informal with little or no documentation, or very formal. The level of formality depends on the context of testing, including the maturity of testing and the development processes, time constraints, safety or regulatory requirements, and the people involved. So on the test development process, looking at the formal test development processes, there are three main steps. Analyze the test bases, identify the test conditions, and document them in the test design specification. Then design the test cases required to test the test conditions and document them in the test case specification. And build the test procedure for executing the test cases and document them in the test procedure specification. So in this graphic here, so the test base, analyze, test, and then test design specification, then design and test case specification, then build test procedure specification, then you can actually test execution. IEEE 829, the standard for software test documents. The standard for software test documentation describes the content of 8 documents to be produced during the software testing. Preparation of tests, the test plan, so plan how the test will proceed. Then the test design specification, which will decide what needs to be tested. And then the test specification, which is create the test to be run. The test procedure, describing how the tests are run. Then the test item transmission report, specify the items released for the testing. And then after the preparation, then it is running the tests. So as you run the test, you need the test log. So record the details of the tests in time order. And then the test incident reports. This is where you record the details of events that need to be investigated, like bugs and incidents. And then after the running the test, you need to do the completion of testing. So the test summary report summarizes and evaluates the tests. Continuing with the IEEE 829, the standard for software test documents. This section I'll be describing the 3 specification documents. The other documents will be covered later. So the test design specification, so documents the test conditions, so the covered items for a test item, the detailed test approach, and the associated higher level test cases. And then the test case specification is it documents a set of test cases, the objectives, the inputs, test actions, expected results, and the executions preconditions for a test item. And then the test procedure specification, which is the documents, the sequence of actions for the execution of a test. If the test is to be executed manually, it is called a test procedure. And if it's executed by automated tools, it is called a test script. Here is a graphical representation of the test phases. So at the higher level, the master test plan. So the test plan, at the test plan level, you'll be documenting the unit test, the integration test, the system acceptance test, the maintenance test. And then following down, the three topics we're going to be talking about mostly on this section is the test design specification, the test case specification, test procedure. So the design specification, it's where the test phases are of the test design unit test, then the test design integration test, the test design system acceptance test, and the test design maintenance test. And then following after that, the test cases. This is where you're going to be breaking down into test cases. So test cases 1, 2, 3, 4, 5, and so on. And then the test procedures. So how you're going to take these test cases and proceed with the tests. And then the actual test execution. So based on all these information above, you go in and proceed with the execution. And then at the end, you will provide the test logs, the test incident reports, all the bugs that you found. And then at the end, when it's all complete, then the test plan execution summary report. So what's a test condition? An item or event of a component or system that could be verified by one or more test cases. The test design specification contains test condition and higher level cases. Example, the system must only allow valid registered customers to order. These give test conditions such as valid customer code, invalid customer code, registered customer, non-registered customer. This will then be combined into high-level test case such as the input of a valid registered customer code, the input of a valid format but not registered customer code. Test case. Test case is a set of input values, execution preconditions, expected results, and executional post-conditions, such as to exercise a part of code. Test cases can be thought as a combination of elements like input values, one or more test conditions already grouped into high-level test cases, execution preconditions, a state of the system prior to test the execution, data requirements, both input and already on the system, expected results, such as a screen display, error display, data storage, and execution post-conditions, a state of system after the test execution. So here's a simple table showing a test case based on the an example as described above. So the test condition versus the input of a valid register customer code. So the input value, for example, AB0001, and then the precondition is a customer AB0001 zone database, and the expected result, customer details displayed, and the post condition, no change. Traceability. Test conditions and test cases should be linked to the requirement to provide traceability. The Y number system is widely using for this type of task. So 1.1, 2.1.1, and so on. So traceability is bidirectional, so it ensures that each requirement is adequately covered by the tests, and each test has a purpose related to the requirement. So here's an example for the test-based requirements 1 to 4, and then a cross-reference with the test conditions put in under the sections. Under each section, there's under like a child section, and a cross-reference with the test cases as well. So all of them should correlate with each other. Test procedure. Test procedure is a sequence of actions for the execution of a test, it should contain all instructions for running the test cases. It's where the test data is and how to load it, logging to the test system, step-by-step instructions to run the test cases, where and how to record and check the test results, action to take to finish test and backup data. So test cases may be grouped together in the single test procedure, but it is often simpler to write a separate test procedure for each test case. Here's an example of a test procedure. So step number one, action. So login with the user ID, for example, ABC123, the password, and the expected result is main menu displayed. So this is a very typical table used for testing. So you have the number of steps, you have the actions, and you have the expected results of the action. And if anything happens that it's out of these expected result, then you write an actual result, make some notes. Reasons to know the test coverage. So here's an example, test completion status. So what it does is it provide a quantitative measure of the quality of the testing that has been done so far. So provides a way of estimating how much more testing is needed. Test execution schedule. The execution schedule is not part of the IEEE 829 standard, but it is widely used by testers. So the order of execution can be based on logical or technical dependencies of test cases, order of business processes of functions, prioritization due to risk analysis, test cycles or phases, for example, in regression testing, and availability of test environment or hardware. So the various test procedures and automate test scripts are subsequently formed into a test execution schedule that defines the order in which they are executed. So you would have like a test case, and then you have a bunch of other test cases that you wanted to run. But within this group of test cases, then you will have a priority to surpass, for example, number 5, and you wanted to go ahead and then test case number 4 due to any of these already mentioned order that you might feel like to do it. Now getting into the three categories of test case design techniques. So the purpose of a test design technique is to identify test conditions, test cases, and test data. So the non-black box technique, white box technique, and experience-based techniques. So what we're going to talk more about in depth in the next future slides. But here is a very summary about black box techniques. For example, it's also called specification-based. It's a way of selecting the test conditions, test cases, or test data based on the analysis of documentation. It takes an external view of the software, so you don't see internally, you just see outside. That's why I call it black box, so you don't have the view internally. And the white box technique, also called as a structured based, this way tested those an analysis the internal structure of the component of the system. So it's white box because you can actually see the codes, and you can see the structure, how the developers has been developed the software. And the other design technique is the experience-based technique. It uses the knowledge, skill, and expertise of testers to the test cases. So under the design, then you see key elements of what to look for when you do the test case design. So functionality, message, professionalism, branding, accessibility, engaging, simplicity, and the usability of the system. Okay, at the specification-based technique, the black box testing, test cases derived directly from a specification or a model of a system or proposed system documentation. So testers can show if meets its specified requirements, but will not discover if the specification is incorrect. It includes both functional and non-functional testing, but it does not test internal structure or component. Five types of specification-based techniques. So all dynamic test levels will include black box testing, functional and non-functional testing based on analysis of business requirements, designs, or specifications. So the five specification-based test design techniques is equivalence partitioning, boundary values analysis, decision table, state transition, use case. Equivalence partitioning. So what's equivalence partitioning? It reduces the number of tests needed by considering partitioning is the only test. Equivalence partitioning. In equivalence partitioning, inputs to the software system are divided into groups or ranges of values that are expected to exhibit similar behavior. So they are likely to be processed in the same way, for example, have the same output. The groups are called equivalence partitioning or classes. Instead of testing every value in the partition, one value can be chosen to represent all and used to test the whole partition. So partition can be identified for ranges or sets of values, outputs, time-relate values, status values, interface parameters, etc. So equivalence partitions can be for valid data. For example, values that should be accepted and invalid data, for example, values that should be rejected. So tests can be designed to cover all valid and invalid partitions. Equivalence partitioning is applicable to all levels of testing and can be used to achieve input and output coverage goals. We got here an example of equivalence partition. So at a minimum, we should test one fail, one pass, one merit, one distinction, rather than every possible score. So drawing a simple line chart can help you identify the partition as shown here. So there are four valid partitions and two invalid partitions, give a total of 6 tests to cover the whole specification. So an application is used to assign grades to students taking exams as follows. To pass, a student must score at least 40. To gain a merit, a student must score at least 60. To gain distinction, a student must score at least 80. Any score less than 0 or greater than 100 is invalid. So there's no point in testing anything less than 0 and no point in testing anything other than 0, apart from identify that this is an invalid partition. So drawing a diagram helps clarify the specification and identify the gaps. So upper, lower boundaries. In this case, the specification did not explicitly state that the output value is for an output less than 40. So the assumption is it will be, fail. Boundary value analysis. Boundaries are divided lines between equivalence partitions. So behavior at the edge of a partition is more likely to be incorrect than behaviors within the partition. So boundaries are an area where testing is likely to yield defects. So look out for that. The minimum and the maximum values of a partition are its boundary values. A boundary value in a valid partition is a valid boundary value. A boundary value in a invalid partition is an invalid boundary values. So tests can be designed to cover both valid and invalid boundary values. It's a bit confused, but more you get into it, more you understand. So boundary value analysis can be applied at all test levels. It is relatively easy to apply, and its defect finding capabilities is really high. So this technique, as known as a boundary analysis, is often considered as an extension of equivalence partition or other black box testing design techniques. So in this example here, there are 5 boundaries, giving a total of 10 tests to cover the whole specification. The diagram also helps to clarify the minimum increment between values. For example, should we test just 39 or 39.9 or 39.99? So it's one thing that I would be raising a question of. Decision tables. Decision tables represent the behavior of a system that depends on the outcome of multiple decisions. They may be used to record complex business rules that a system is to be implemented. The table specifies the possible combination of conditions and the resulting actions according to the business rules. Each column of the table corresponds to a business rule that defines a unique combination of conditions and which result in the execution of the actions associated with that rule. Conditions are usually stated in Boolean form, for example, true or false or yes or no. The process of creating a decision table is as follows. Identify the conditions, the stubs, so like a description from the test basis. Identify the action stubs descriptions from the test basis. Establish the condition entries, all the possible combination of conditions. List the rules from the test basis and work out the action entries for each rule, the outcomes associated with each combination. And each column corresponds to a test case in which the condition entry are the test conditions and the action entry are the expected results. If there are 2 conditions, then there are a maximum of 4 possible combinations, and for 3 conditions, there can be up to 8 possible combinations. If n is the number of conditions, then math would be a number of possible combinations equal to n. So let's work in this decision table example. The requirement is delivering goods from warehouse to shops. For each shop's delivery schedule, we look to see how far away the shop is from the warehouse. Then we go through each item on the schedule. If the shop is further than 10 miles away, we add the item to the next weekly delivery for that area, unless it's a rush order, in which case we send it by overnight carrier. When we have an item to be delivered locally, for example, less than or equal to 10 miles, we add it to the next day's delivery, unless it's a rush order, in which case Joe delivers it with a state car immediately. So this can be represented as a decision table, just like this one in the example. So if you look at it, the broke down by the lines and the rules. So in this example, each combination of conditions has a specified action and every combination is tested. Often, however, there will be combinations of conditions for which there is no specification action or a specification generated. Then the tester will have to decide how many to test based on risk. When faced with complex requirements, it is often easier to understand the logic using a diagrammatic technique, in this case a decision table. Like EP and BVA, it also helps to clarify the rules and establish any omissions of ambiguities. The strength of decision table testing is that it creates combination of conditions that might not otherwise have been exercised during the testing. Here's another example of decision table. So the requirement is delivering goods from warehouse to shops. For each shop's delivery schedule, we look to see how far away the shop is from the warehouse. Then we go through each item on the schedule. If the shop is further than 10 miles away, we add the item to the next weekly delivery for the hour. Unless it's a rush order, in which case we send it by overnight carrier. When we have an item to be delivered locally, for example, less than or equal to 10 miles, we add it to the next day's delivery. However, all items that are over the weight limit will need to go by special delivery. So if this example is extended to include the third condition, then the number of action columns should expand to 8. However, there are shortcuts which allow columns to be combined if they have the same outcome. So the indifference symbol, minus, means either yes or no. The else symbol, marked by E, indicates any other combinations not explicitly specified in the business rule. Use of indifference and else reduces conditions entries but increase the risk of missing something. State transition diagrams table, state transition testing. Some system can be described in terms of states or modes that the system can assume, together with the events that cause a change from one state to another. These systems can be represented by a state diagram showing the state a component or system might be in, the transitions or changes between states, the events or circumstances that cause transitions. So the states of the system or subject on the tests are separate, identifiable, and finite in number. State diagrams are often used for digital systems, embedded software, or technical automation in general. However, the technique is also suitable for modeling a business object having specific states or testing screen dialog flows. Example for internet applications or business scenarios. State transition testing is a test design technique in which test cases are designed to execute valid and invalid state transitions by creating state table showing the result transitions for each state combined with each possible event, showing both valid and invalid transitions. So the state transition diagram shown in this operation of a digital clock. States are shown by a box or circle with the name of the state. Transistors are shown by arrows indicate the change of state. Events which cause transitions are shown by text on the arrows. Test case can be derived from the state transitions diagram. To exercise each of the possible transitions by creating a state matrix for every valid transition or arrow. The start state and event represent test conditions, and the finish state is expected results. So creating a test case to cover each possible valid single transition in the model is known as zero switch coverage. It provides the ability to detect the most obvious faults, but will not detect more suitable ones, and which would only be detectable by exercising sequences of transitions. So N-switch or Chol switch testing is a form of state transition testing in which test cases are designed to execute all valid sequences of n+1 transitions. Therefore, zero switch testing means covering 0 plus 1 or single transitions. The state matrix showing only valid transitions down on this table. However, if we wanted to show both valid and invalid transitions, we will need to create the state table. The table is filled in with the outcome of performing each transition from each start state. If this result is unknown or not shown on the state diagram, the corresponding cell is left blank or marked as null to indicate an invalid transition. State tables are therefore useful testing aid to derive the invalid null transition directly. The decision whether to test invalid as well as valid transition will depend on the context and risk. Same state transition. Events that cause a system to remain in the same state are shown with a recursive arrow. These state transitions must also be included when defining test cases. For example, in the diagram below, if you press the skip button on the MP3 player, while it is playing, it will start playing the next track. When testing valid transitions, zero switch transition on a straight transition diagram, a same state transition counts as one, just like any other arrow. This illustrates that state transitions do not show all system functionality, only transition between states. Sometimes outcomes are shown on diagram under the arrows, or there may be a separate text description accompanying the state diagram, which should also be used as a test basis. Use case testing. Use case testing is a black box testing design technique in which test cases are designed to execute scenarios of use cases. So use case, a sequence of transactions in a dialogue between an actor and a component or system with a tangible result, where an actor can be a user or anything that can exchange information with the system. Quote by ISTQB in 2010. So use cases are a way of defining high-level requirements or business processes viewed from a user perspective. They may be described at the abstract level, business use case, technology-free business process level, or at the system level, system use case on the system functionality level. Contents of a use case testing. The structure is very similar to a test procedure script, so is ideal for design test cases, particularly with UAT with customer or user participation. Process flows in a use case are written based on intent use, which makes them very useful for designing acceptance testing by end users. The descriptions could act as the test procedure, thus minimizing test development costs. However, they are detailed enough to test properly and therefore uncover errors. Use cases can also uncover integration defects which individual components tested would miss. So actor list, pre and post condition, mainstream, more likely scenario, alternate scenarios, and exception. Structure-based techniques, also called white box techniques or white box test design techniques, used to explore the system or component structures. The extent of the coverage of the software can be measured for existing test cases, and further tests can be delivered systematically to increase even more coverage. So white box testing, it's a test that you can see the codes, you can read the codes, and you can test at the code level. White box techniques. It can be applied at all test levels, whatever the system can be represented in a structure or architectural diagram. So component level, the structure of a software component, for example, statements, decision, branches, or even distinct paths. Integration level, the structure may be a call tree, a diagram in which modules can call other modules. System level, the structure may be a menu structure, business process, or web page structure. Measurement of code structures in a very comprehensive form of testing, but can be complex, time-consuming, and resource-intensive, and may be too detailed for many businesses. It is most likely to be conducted where extremely thorough testing is required, such as safety critical systems, defense control system, medical equipment, software it's required. So white box testing is also called structural testing. So structural testing coverage is the key concept in structural testing is coverage. So coverage is expressed as a percentage of a structure covered by tests, and all white box testing can be used to measure coverage of a structure. There are different coverage measures of software code structure, so statement coverage, decision coverage, condition coverage, multiple condition coverage, all paths coverage. So as you can see, the arrow here pointing down, which means the weakest coverage point is the statement coverage. As you go down to the options of coverage, as you do the all paths coverage is the strongest coverage of them all. We only need to know techniques for statement and decision coverage at foundation level, but we need to be aware that strong techniques exists. Statement testing and coverage. A statement is an atomic action, a single instruction to the computer. For example, gross amount equal net amount plus tax. Test cases are devised to execute a specific executable statements at least once. This approach does not ensure complete coverage of functionality, but it does provide a level of confidence that simple code errors have been detected. So this is another example. Statement coverage equal number of statement covered divided by total number of statements multiplied by 100. Decision, testing, and coverage. A decision has two possible outcomes, true and false. For example, if a value between 50 and 16, then do action A, else do action B, and if. So test cases are devised to execute a specific decision outcome of branches. So statement coverage equal number of statements executed divided by the total number of statements multiplied by 100. All decisions are statements, so 100% decision covered guarantees 100% statement coverage, but not vice versa. Decision testing is a form of control flow testing as it generates a specific flow of control through the decision points. Note that in the example above, it is not necessary to test equivalence partition or boundaries for this level of structural testing. Just one value in the range through and one outside, which is false, would be enough to achieve 100% decision coverage. So 100% coverage doesn't necessarily mean exhaustive testing. Here's an example of statement and decision coverage. Software source code and flowcharts can both be used to assess coverage. So in test 1, using a value of 3 for x will cause the condition if x less than 5 to evaluate to true. So executing the statement y equals 0. This test executes all these statements, so has achieved 100% statement coverage. Test 2, using a value of 8 for x, will cause the condition to evaluate to false, so the system will jump directly to the end if statement, skipping the line y equals 0. Both tests are required to achieve 100% decision coverage. So full statement coverage can be achieved without exercising all the software structure. This is why statement coverage is considered the weakest coverage measure, and decision coverage is a stronger measure. Here is another example of statement and decision coverage. Consider the following code segment. If y is greater than 10, then z equal x divided by y, else z equals y divided by x, and if. In this example, there is statement on both the true and the false branches. So two tests are required for 100% statement coverage, as well as for 100% decision coverage. So what about loops? Loops are an important software construct, but counting path for white box testing doesn't work quite the same way for loops as for simple if decision. For example, this, if the while decision outcome is true, when it's evaluated the first time, then control passes through the true branch and loops back to the decision, where it is re-evaluated. As long as it remains true, the loop will continue. When the decision outcome becomes false, control passes out the loop to the statement after it. This means that both the true and false branches can be covered by a single test, which can never happen if decision. Note that this assumes the loop is not infinite. If the decision is true the first time, it will eventually become false. If the while decision outcome is false, when it's evaluated the first time, then the loop is never entered. The flowchart for loops looks slightly different from if decision, as the decision diamond has two control lines flowing into it, one from the preceding statement and one from the end of the loop. Experience-based techniques. Experience-based testing is where tests are derived from a tester's skill or intuition and the experience of similar applications and technologies. It is not based on analysis of specifications or structure. It is generally less thorough than systematic techniques like black box and white box, but it can be more effective if there is a lack of testing time or resources, and it can identify special tests not easily captured by formal techniques. Testers use the expertise to identify key areas to test, such as critical or most used functions, areas most likely to fail, for example, like defect clusters or complex code. Experienced test designers are best suited for this approach, which is, if it's possible, should be used to augment the systematic techniques. It may be much less effective for inexperienced testers. Error guessing. In error guessing, testers use the knowledge of the system and testing to anticipate possible defects. They design tests to target known or suspected weakness or addresses aspects of the system that have caused problems in the past. Testers should think laterally and consider how users could use the system, not just how they should use it, which, the aim is a specification-based testing. So error guessing can often be used after black box testing to cover specific problems areas more thoroughly. The success of error guessing depends on the knowledge and skill of the tester, but the effectiveness can be improved if several testers, users, or developers contribute to identify the possible errors. Fault attack. A structured approach to error guessing, called the fault attack, is to enumerate a list of possible defects and then design tests to force each one in turn. These defects and failure list can be used on experience, available defect and failure data, common knowledge about why software fails, a list of error messages from program specification, ideas from groups of testers, users, and developers. Exploratory testing. Exploratory testing combines testers' experience with a structured approach. Testers explore the software and learn about it by testing. The technique involves concurrent test design, test execution, test logging, and learning based on a test charted containing test objectives and carried out within time boxes. It is an approach that is most useful where there are few or inadequate specifications and severe time pressure, or in order to augment or complement other more formal testing. It can serve as a check on the test process to help ensure that the most serious defects are found. Exploratory testing is not purely random or ad hoc, as it involves a high-level plan and all test activities, like design, execution log, incidents. It must be documented. But unlikely specification-based testing, exploratory testing deviates from the scripts to explore areas of interest and learn more about the system. It may be used on its own or in conjunction with other techniques to ensure that testing is focused on the most important area and identify possible problems. Exploratory testing is common within agile methodologies, which often incorporates limited specification documents with a short development timescale. Here is an example of exploratory testing process. So number one, start with a higher level test design, as there is a limited or no specification. This may be just to explore basic functions such as user input, or to follow the happy path processing where no error conditions are met. This must be documented in a test specification like black box testing. Then number two, execute the tests and log the outcomes. Number three, investigate any unexpected results. In standard black box testing, these would be recorded as incidents, and the rest of the scripted test would be executed as planned. But in exploratory testing, the plan is suspended and the new tests are designed to explore the anomalies and learn about their cause. Deviating from the plan to explore areas of interest is sometimes called the toolbox principle. Number four, document all test designs and results so that the tests are repeatable. This also increases the documented knowledge about the system. Choosing test techniques. So according to the ISTQB, studies have been unable to prove conclusively that one type of testing is better than another. So it is important to select the most appropriate depending on circumstances. The choice of which test techniques to use depends on a number of factors, such as type of system and regulatory standards, development life cycle and test level, customer requirements, contractual requirements, level and type of risk, test objective, documentation available, knowledge of the testers, time and budget. So for example, the factor of using a web-based system, the appropriate test technique would be a state transition testing, and the rules-based requirements, decision table, high risk or safety critical, it's indicated that you use white box testing, detailed specification, black box testing, unavailable specifications, exploratory testing, availability of source code, white box testing. agile methodology or limited time, experience-based technique. Choosing the best test technique. Some techniques are more applicable to certain situations and test levels. Others are applicable to all test levels in general. So specification-based techniques are used in sequential development models at all levels of testing for business critical system. So structure-based techniques are used mostly at lower test levels, component testing, component integration testing, and is indicated for safety critical systems. Experience-based techniques are used to augment systematic techniques in iterative agile development models. When creating test cases, testers generally use a combination of test techniques to ensure adequate coverage of the object in the test. Now we came to the end of the section 4. So in summary, what you have learned so far is the test condition, test case, test procedure specification, and test coverage. 3 categories of test case design techniques: white box, black box, and the experience-based technique. So specification techniques such as equivalence partitioning, boundary value analysis, decision table testing, state transition testing, use case testing. You learn as well structure-based techniques known as white box testing statement or decision testing in more depth. And finally, using error or exploratory testing, applying experience-based technique. Okay, well done. So now you complete this section 4. Make sure you go down the attachment and get the quizzes and practice. Practice now while your memory is still fresh, so you can get the most of the section itself. So now is the end of section 4. We're gonna move on into section 5. Before that, if you have any questions, drop down me a question here. If you have any comments about the video, about all the material and the information, please do so as well. It helps me improve it, make it better for this one and for the next material I'm planning to release soon. And then if you really like it, thumbs up, share with your friends, share with family, share with everybody, across network, everywhere. And that's it. Let's move on. Let's go for the next one. 4 is done. 5, 6, next.